going to take another look at electric field on charges and force electric on charges and volts on parallel plates today. So let's get started. Let's say I've got a charge here, and let's make this charge here a plus 2q, and make this one over here just a minus q. Now remember, if these are conducting spheres, that charge is going to reside on the outside, but all of it's going to look like it's coming from one dot in the center. That's where we'll make all of our measurements from. Let's take a look at our electric field equation. So electric field is going to be K Q over R squared for point charges. Now remember, we pretend to put positive test charges between them. So let's say I put a positive test charge here. Well, we do apply the superposition principle. There are two things going on here. This charge here is going to try to push this charge to the right. So let's call this electric field number 1. Okay, now remember, you're going to use K, this Q, divided by the distance between this test charge and that center, squared. Okay, so that's electric field 1. Okay. This one here is also a negative, so it's going to attract it. So I'll draw a second vector here. Okay, and that's going to be electric field 2. Okay, so the net resultant for this, once you calculate the same equation, again, the distance from the center of this to that point charge is going to be the radius. And if we're right in between, right in the middle, you're going to get a bigger electric field push to the right from this charge versus the attraction from this. So electric field total, we'll just say electric field resultant, would equal E1 plus E2. And you'll never be able to get electric field equal to 0 between these two types of charges here in the middle of it. So now what if I put my test charge over here? Well, this 2q is still going to push this one to the right. I'm going to draw a smaller vector because that's going to be a lot less. So we'll call that E1. But this charge is going to attract it to the left. And that's going to be E2 then. Okay, so now we have the resultant is going to then be E1 minus E2. And you've got to use this equation twice. For this one, you're going to use the 2q for the charge, k is our constant, divided by r squared, the distance from the center of this to that test charge. And likewise for E2, you're going to be using this charge here, just 1q, and the distance from here to there as your r. Okay, there is a place here where you could get net electric field equal to 0. Because if E1's value is equal to E2, okay, it's possible, but it'll depend on how much charge you have here, okay? I don't know if it's possible with what we've got written here, but this guy's got to be a lot larger now because you're much closer to this one here. Likewise, on this side, you'll never be able to get an electric field equal to 0 over here because this charge is larger than this one here, so it's not possible because the value for this one here, the electric force per charge is always going to be much greater here than it would be here because you're closer to a larger charge here, so you can't get it equal to 0. Now what about, let's say I make a positive 2q here and a positive 1q here. When I put my positive test charge in the middle here, I'm going to do my superposition principle again using this equation. This charge here is going to repel that positive test charge this way again. We'll call that E1. Okay, and then this one is also going to repel it, but it'll go in the opposite direction here. E2. Okay, so then my net electric field, ER, is then going to be E1 minus E2. Okay, and there would be a place in between these two okay, that I could get an electric field equal to 0. Okay. So, but what if I put a positive test charge here? Okay, well, this one's still repelling it that way. Let's give that an E1. Okay, but that one also, okay, is repelling it to the right. Let's call that E2, to the right this way, if my positive test charge is there. So then E resultant is going to equal E1 plus E2. And there's no way then to get that electric field equals 0. Likewise, if I put it over here, we're going to get a repulsion that way and a repulsion that way. And E1 will end up negative going to the left, but it can't equal 0. So charges are not the same. You can't get electric field equal to 0 in between them, but you can on one side of them. If the charges are the same, you can get electric field equal to 0 between them, but you can't on the outside of them. So that's kind of how that works. And in the next video, we'll talk more about electric force and voltage.